Okay, welcome to the last class of this course. So today we will finish up with the organometallic reactions, more precisely with the applications of organometallic reactions in catalysis. So in the last class we have already discussed a number of these. In the last one we discussed was the catalytic olefin hydro formulation, and we have seen that we can produce aldehydes starting out from an alkene in the presence of carbon monoxide, hydrogen, and a carbonyl hydride as the catalyst. And we've also looked at the reaction mechanism, which you still see here. So what we add to the reaction mixture is our cobalt, a dimer cobalt carbonyl, which then in the presence of hydrogen forms the carbonyl hydride, which is the actual catalyst. And then through various reaction steps, we form our aldehyde from the alkene and carbon monoxide and hydrogen. So this mechanism is called hydroformylation. It was invented, I believe, in the 1940s at BASF, and since then this chemistry has expanded, and there are several variations of the hydroformylations, which are generally called hydrocarbonylations. So one of them is the hydrocarboxylation, and in this case react the alkene with carbon monoxide and water instead of hydrogen, and because of the presence of water you then get a carboxylic acid, as you can see here, instead of an aldehyde. So when you replace the hydrogen with an alcohol, and that's actually not correct here, so this needs to be an alcohol and not water, then again in the presence of carbon monoxide and carbonyl catalyst, you get what is called a hydroalkoxycarbylation, and this reaction is then useful to make an ester. And lastly, you can also replace the hydrogen by an amine, and then you have a so-called hydroamide carbonylation, and this produces you actually an amide from an alkene, carbon monoxide and the amine. Okay, so these were hydroformylations and hydrocarbonylation reactions that use carbonyl catalysts. Let's look at another industrially applied process, which is the Monstadtacetic acid process. So this is the industrial process to make acetic acid at large scale. And in this process, you start out with methanol, and again, you're using a carbonyl catalyst, in this case, in conjunction with the co-catalyst, which is HI, and carbon monoxide, in order to make acetic acid. Okay. So now, how does this reaction work? So in the first step, there is a reaction between methanol and HI, and well, you can get nucleophilic substitution of the OH group by the iodo group, which then forms methyl iodide. And water is getting eliminated. Of course, that's an equilibrium reaction here. Now this methyl iodide, which is in the chemical equilibrium, can now react with the rhodium catalyst, which you see here. So this is a square planar catalyst with rhodium in the oxidation state plus 2. So now the metal iodide can react with this catalyst to form this compound here. So now you have learned a lot about organometallic reactions. Maybe one of you can tell me what type of organometallic reaction is this step? Nobody having an idea? Having an idea? Please don't be shy. So this is an oxidative addition. Okay, so we are adding the metal iodide. Okay, so the reactant state breaks apart, and we're getting an oxidative trans addition in order to be precise. So that adds, well, 2 negatively charged ligands. So in this case, we have rhodium in the oxidation state plus 4. Okay. So now this species here can now further react to form this species here. Do you know what type of organometallic reaction this is?
Is that one a migratory insertion?
Yes, correct. So this one is a migratory insertion. In particular, this is well, a carbonyl migratory insertion. So we have here this neutral carbonyl in cis position relative, in this position relative to the methyl group. Okay, so the CO unit inserts in between the rhodium and the methyl group, and then this gives this acetyl group here. Okay, so now you see that this creates here a vacant site. The rhodium here is in the coordination number 5, and in the presence of carbon monoxide, this 6th position now can be filled with carbon monoxide. This also serves as the driving force of the reaction, because I've said that these migratory insertions are actually reversible reaction. So by occupying the empty site with new carbon monoxide, we're actually shifting the chemical equilibrium here to the right side. So now, what is the next step? The next step is the elimination of acetyl iodide. Can you tell me what kind of reaction that is? Yeah.
Is it a reductive elimination?
Yes, correct. So that's reductive elimination. We eliminate a ligand at the same time. We also reduce the rhodium. So rhodium here goes from the oxidation state, well, plus 4 back in the oxidation state, plus 2. Okay, so that regenerates our catalyst. Okay, so now we still do not have actually acetic acid. So what can happen next? Well, this acetyl iodide is in a reactor that also contains methanol. Okay, so now what can happen is that, well, the iodide group, okay, can react with methanol to then give acetic acid, and methanol is being converted into methyl iodide, so the OH group gets substituted by the iode group. So now we have formed additional methyl iodide, and that can now restart the catalytic cycle. So this methyl iodide can now react again with this regenerated catalyst, and another catalytic cycle can form, producing more acetic acid, and the process proceeds until all methanol and all CO is converted into acetic acid. Okay, so this is the Monsanto acetic acid process. Now let's look at a last kind of reaction and its application, which is the olefin metastasis. So in an olefin metastasis, we we cleave the carbon-carbon double bond of an alkene, and then we reconnect the resulting fragments in a different way. And for that, again, we need a catalyst, which basically cleaves us the carbon-carbon bond in the middle and reforms new carbon-carbon double bonds. So in this case, you see on the left side here, this olefin has this red part and the blue part. So we formally cleave that molecule in the middle, and then we connect, well, two red parts together. Okay, that is forming this molecule, and two blue units together to form that molecule. So again, we are producing olefins, but we are producing new olefins from an reactant olefin. So this kind of reaction is also typically a chemical equilibrium that does usually not lie on one particular side. So again, it needs actually special tricks in order to make the chemical equilibrium shift to the right side, and we are going to discuss these tricks in a moment. Okay, so this olefin metastasis was invented by Richard Schrock and Robert Grubbs, who developed these catalysts that make the olefin metastasis happen. So Richard Schrock developed molybdenum carbene catalysts that have here this a molybdenum carbon double bond, and Robert Grubbs developed another type of alkene catalyst with ruthenium and bulky phosphines here as a ligand, whereas the Schrock catalyst has here these amido ligands attached to this. So the Schrock catalysts have the advantage that they're actually more reactive, but they're also very touchy, so they're very air and moisture sensitive. So the Grubbs catalysts are a little bit more practical. They are not as sensitive, but they're also not quite as reactive. Both Richard Schrock and Robert Grubbs received the Nobel Prize in Chemistry for these catalysts in 2005. Okay, so now what is the scope of olefin metastasis? Let us discuss that now. And a very common reaction is what is called irregular metastasis with terminal alkenes. Okay, so the carbon-carbon double bond is actually at the terminal end of the molecule. So why is this particularly attractive? This is because as you perform the olefin metastasis, we are producing ethylene as the byproduct. And that ethylene is a gas and can be removed quite easily from the chemical equilibrium. And because of that, we can fairly easily shift the chemical equilibrium to the right side. And this produces our target product molecule here in a high yield. So there are other variations of the theme possible. So one variation is what is called the acyclic diene metathesis, which is also called ADMET, and this is a reaction which produces polymers from terminal dienes. So here's an example for that. Here we have a diene with 1, 2, 3, 4, 5, 6, 7 carbon atoms. Okay, and you see that both carbon-carbon double bonds are at the end of the molecule. So as we do olefin metathesis, we cleave the carbon-carbon bonds in the middle here and here, and reconnect the fragments in a different way. So that again produces ethylene, and the ethylene can be driven off from the reaction mixture quite easily, and that serves as the driving force for the reaction, shifting the chemical equilibrium to the right side. And in this case, we are forming this unsaturated polymer here, where basically the carbon-carbon double bonds are separated by 1, 2, 3, 4 carbon-carbon single bonds. Okay, of course, this has a great scope because we can easily modify the unit in blue here and produce unsaturated polymers of a great scope. Okay, so what else can we do with olefin metathesis? We can also have what is called a ring opening polymerization reaction. This is called ROMP. Okay. So in this case, we start out with a strained olefin. So for instance, norbornene is a strained olefin. And as we perform the olefin metathesis, we actually release the strain by opening the ring, cleaving the carbon-carbon double bond here, and again connect the fragments in different way. So here you see that no ethylene as a byproduct is produced. In this case, the chemical reaction is shifted to the right side because the reverse reaction is unlikely because it would form a strained ring. So the driving force for this reaction, in this case, the release of the ring strain. So you can also do the opposite. We can also form rings. When these rings are thermodynamically stable and also formed kinetically easily, and this is then called the ring closing metathesis. So for instance, we can perform this reaction, forming this unstrained ring here with this carbon-carbon double bond. So this reaction can occur when you react this diene here. Okay, and this diene here is again terminal alkene. fragments, but you see that these fragments are now 1, 2, 3, 4, 5 carbon atoms apart, so that when you actually cleave this carbon-carbon double bond and this carbon-carbon double bond, an unstrained 5-membered ring like this can form quite easily. So in this case, you again get ethylene as the byproduct, and that byproduct can leave the reaction equilibrium fairly easily. And that again drives the chemical equilibrium to the right side. Okay, so now we have looked at the synthetic scope of the olefin metastasis reaction, but we actually do not know the mechanism of olefin metastasis using the catalysts yet. And this is what I would like to discuss the last. So here's the mechanism. So the reactive part within the catalyst is actually the carbene unit, okay? Where you have a double bond between the metal and the carbon. And that carbene unit can undergo a 2+2 cycloaddition reaction with the reactant olefin. Okay? So that means that this electron pair here reacts with this carbon to make a carbon-carbon single bond. And this electron pair here in the other carbon, in the carbon-carbon double bond, basically reacts with the metal in order to make another carbon, to make a carbon-metal single bond. Okay, so what you get is therefore a strained, highly strained 4-membered ring. Okay, so this reaction is of course, well, reversible. So there's a chemical equilibrium between this 4-membered ring and the reactants. Okay, so the ring can just reopen the way it has formed. However, it can statistically also open in a different way. Okay, so this electron pair here can actually move here to make a carbon double bond here, and this electron pair here in this single bond can move over here to make a metal carbon double bond. Okay, so that actually forms our first reaction product. Okay, our first new alkene. Okay, and we've actually formed an metal carbene back. Okay, so you have actually here a similar species in comparison to over here. So therefore, the new carbene complex here can, well, react in a similar way. So that means that it can react in another 2+2 cycloaddition reaction with another reactant molecule, as shown here, to make another 4-membered ring, as shown here. So again, this is a chemical equilibrium reaction. So this 4-membered ring can just open the way it has formed. However, it can also open in an alternative way. So this electron pair here can move over there, making again a carbene complex. And this electron pair here can move over there to form now ethylene. And our ethylene is now our second reaction product. Okay, so now as the process happens, we again form a carbene complex, and our catalytic cycle is closed, and the new carbon complex can again react with this new starting molecule to make the catalytic cycle happen another time, and that happens over and over again until the reaction is complete. Okay, so this is what I wanted to tell you. We are now actually at the end of this class, so I can just stop the recording here.